Hello once again, and welcome to our series on statistics. My name is Manny. Today's topic is random variables. We want to study the notion of a random variable and give some illustrations. Now let's look at what a discrete random variable is like. Tossing two fair dice, X denotes the sum appearing. Concert attendance, X is the number of people showing up at a concert on a particular night. 4-card hand poker, X denotes the number of aces appearing, 3 aces for example. X denotes the number of cars sold in a week. Could be the number of rooms rented at a hotel during a weekend. Number of well drillings, and the number being successful in a region. And we're going to look at a particular case of the well drillings. Suppose, for example, this data comes from an oil and gas company. We see here the number of drillings taken and the frequency of successes, and we can look at the frequency distribution and the relative frequency distribution, and this becomes a random variable X, and we can just simply add probabilities as seen on the screen here. Now we're going to look at the notion of tossing two fair dice. We want to know what the expected value is if we receive in dollars the amount showing in the sum of the two dice. So look here, to get the sum of 2, it's 1, 1. 3 is 1, 2, 2, 1, and so on. Now feel free to pause the screen and follow along in the handout. Now you can see here there's 36 events in total. They're equally likely cases, so the probability of any one of these appearing is 1 in 36. So to get a 2, of course, is 1 in 36 is coming on the screen here in just a minute. Here's the sum in dollars. 1 in 36, 2 out of 36, and so on. And we're simply adding up the number of simple events as shown here. And once we finish this, we're going to plot the distribution. Note the sum of these probabilities must equal 1. And here's the distribution. And we're going to try and find the expected value. The expected value is a summation of X times P of X. Over here in the screen it's this column times probability of X. Now watch what happens here. We're computing X times P of X here. You can do this on your calculator at your desk. And the sum of those is 7. And you'll notice that the expected value is 7. That corresponds to this peak in this distribution here. And that's what we're trying to get at here. So we can say that on average we can expect to earn $7 per trial over the long run. Now we're going to look at the standard deviation, which is the variability above the mean. And here's the formula. Notice the difference between X and mu sub X squared times the probability, or the frequency, relative frequency. If we expand that, we get this expression. And now we need these two terms here. Note X P of X we already have is 7. So we need this X squared P of X. And it's coming on the screen here now. We need this extra column here, X squared P of X. And we're multiplying X squared times P of X. And again, you can pause the screen and write this down in your notes there. And that summation, X squared P of X, is given here. Calculating this frequency, or this number, 2.415. It's the variability about the mean. And we're going to compute the boundaries of this red arrow here. 7 plus or minus 2.4. That's 4.6 to 9.48. Here they come on the screen here now. So we're saying not 68% of the time we can expect to make a value between 4.6 and 9.4 dollars. And so that is those are the statistics involved, and a reasonable price to pay is $7.50 or around there. Now here's another example. Tossing two fair dice, $50 for a pair of sixes, $20 if the sum is 7, but you have to pay $10 to play the game. So we set up the table. Now we're going an event, then the example, and then the win-loss. Pair of sixes, sum is 7, and other, of course, is a loss of $10. Now P of X, of course, is 1 in 36 to get a pair of sixes. Sum of 7 is 6 out of 36. and the other is just 1 minus the sum of the two above it. And the total must be 1 for this column. xp of x is coming on the screen now, minus 5.278, and this is called the expected value. And so we can expect a loss on average per game in the long run of $5 and about 28 cents. Now the standard deviation is coming on the screen here now, suggests that we compute this extra column here, x squared p of x is coming on the screen here now. X squared p of x, summation 141.6667. Putting that in the equation, we get a standard deviation of 10.668. Now, this is certainly discrete, and you can see it's certainly not normal, and so we can expect to lose $5.28 per trial on average in the long run, but this can vary by as much as plus or minus 10.668, about the mean, with a certain degree of reliability. And we're saying here that we have to use Chebyshev because we can't use the normal distribution or the empirical rule. And that's the end of presentation 5.1. We ask you to take notes as required and continue to presentation 5.2.